So in the time it takes you to blink, which is, about 300 milliseconds, your computer just traveled across an ocean.
Right.
It negotiated this wildly complex cryptographic handshake, fetched millions of bytes of data from some cold database, and painted a million pixels perfectly on your screen. And you do this dozens, maybe hundreds of times a day.
Yeah, it's constant.
You just type a URL, hit enter, and boom, a whole universe of information just appears. So today, we're going to freeze time. We're going to take those 300 milliseconds and just, stretch them out to explore the hidden architecture of the web.
I love that framing.
Welcome to today's deep dive. We've been looking through this really fascinating source document called Chapter 1, How the Web Works, Point PPTX, which covers the exact blueprints of web requests. And our mission today is to essentially demystify this incredible global relay race that happens every single time you browse.
What's fascinating here is that we've become so accustomed to the immediacy of the web that we assume it's just, a direct localized connection.
Not like plugging in a cord.
Exactly. But behind that illusion of instantaneous magic is an incredibly aggressive, highly choreographed engineering reality. When you hit enter, you are kicking off a remarkably intricate round-trip sequence involving dozens of completely disparate machines.
Okay, so let's track the very first step of that sequence. When I type a domain name like www.google.com into my browser, which the source calls the client, how does it actually know where to route my request?
Well, that's where DNS comes in.
Right, the domain name system. And I want to push past the standard, slightly tired analogy that DNS is just the internet's phone book. Because looking at how it actually works, it seems much more like a massive, globally distributed game of telephone.
It absolutely is, yeah. The phone book analogy really undersells the engineering involved. At a foundational level, the internet routes traffic using IP addresses.
Right, those unique strings of numbers.
Yeah, like 14.217.234.18. Your browser desperately needs that IP address to reach the specific server. But the problem with a centralized phone book is that if, say, billions of people try to open it at the exact same millisecond, the whole system just collapses.
Oh, right. It would just melt the server.
Exactly. So DNS operates through these recursive lookups and intense layered caching.
Okay, so when my browser asks for Google's IP address, it doesn't just go to one master server, right? It checks its own internal memory first.
It does.
And if it doesn't know, it asks my computer's operating system.
Spot on. And if your OS doesn't know, it asks your local internet service provider.
Wow, it really is a chain.
It is. And if your ISP doesn't know, it queries a global root server, which then points it to a top-level domain server, which finally points to the authoritative name server for that specific site.
It sounds like it would take forever.
It would, but the genius here is something called TTL, or time to live.
Okay, what does that do?
Well, once your ISP goes through all that trouble to find Google's IP address, it remembers it for a set amount of time. It caches the answer. So the next 1,000 people in your neighborhood who ask for Google get the answer instantly from the local ISP without having to, bother the global root servers.
That makes total sense. I mean, it prevents huge bottlenecks.
Yeah.
Like having a smartphone contacts list, you don't memorize your friend's 10-digit number, you just tap their name.
That's a perfect way to look at it.
But it brings up a broader question about the whole architecture. If computers inherently only speak in numbers, and the entire physical infrastructure of the internet is built on these numerical IP addresses, why did we even invent domain names? Was it purely just because human memory is flawed and we're terrible at remembering strings of digits?
Human memory is a factor, sure, but the real reason is infrastructure flexibility.
I mean,
well, IP addresses are directly tied to physical network locations. If a massive company needs to upgrade their server racks or change hosting providers or distribute their load across multiple data centers globally, their underlying IP addresses are going to change constantly.
Oh, I see. So if we only used IP addresses, every time a company moved a physical server, we'd all get dead links until they published their new numerical address in the newspaper or something.
Precisely. DNS decouples the human-facing interface from the underlying hardware. You can completely rip out and replace a data center on the back end, update your DNS records, and the end user typing the domain name never notices a thing.
That is so elegant.
Yeah, the domain name is just this abstraction layer that protects us from the chaos of physical hardware changes.
Okay, so DNS got us to the exact machine. We've routed our request across the globe to the correct server. But that single server is, like, a total workhorse.
Yeah.
It might be handling incoming emails, transferring backend files, and hosting multiple websites all at the exact same time.
Oh, absolutely. It's doing a million things.
Right, so when our tiny data packet hits the server's network card, how does it know which specific software process to wake up? Our sources introduce the concept of ports here.
Yes. So if the IP address is the building itself, the port is the specific apartment number or service entrance.
Okay, I like
The
that.
network traffic sorting is handled by these designated port numbers. They basically tell the server's operating system exactly where to route the incoming data packet so the correct application can actually process it.
And looking at web traffic, our blueprints highlight two major service entrances. There's port 80 for HTTP and port 443 for HTTPS. And it describes HTTP on port 80 as being entirely unencrypted, plain text.
Yes, completely open.
Okay, let's unpack this. If sending data over port 80 is essentially like mailing a transparent, unlocked envelope through the postal service, where literally anyone, your ISP, some random router along the way, a bad actor on your local Wi-Fi, can read exactly what you're saying, why does that door even exist?
It seems crazy now, right?
Yeah. Like, why wouldn't the architects of the internet just default everything to the secure port 443 from the very beginning?
If we connect this to the bigger picture, we have to look at the historical context of computing power. Back in the early 1990s, the web wasn't built for e-commerce or private banking.
Right, it was just text pages.
Exactly. It was a tool for physicists and academics to share public research documents. In that environment, encryption wasn't just unnecessary, it was mathematically and computationally expensive.
How about? Because scrambling the data takes work.
A lot of work. Scrambling and unscrambling data requires CPU cycles. For early servers, encrypting every single public web page would have ground the entire system to an absolute halt. Port 80 was designed for a time when open access and speed were the absolute defining priorities.
That's fascinating context. But obviously today, CPU cycles are incredibly cheap and data privacy is paramount, which is why the source really emphasizes port 443 and HTTPS, where the S stands for secure.
Exactly. When your browser knocks on port 443, it doesn't just send a simple request for a web page. It initiates a TLS handshake, transport layer security.
This sounds intense.
It is. This is where the magic really happens in those 300 milliseconds. Before a single piece of actual web data is exchanged, your browser and the server engage in an intense cryptographic negotiation.
Right, they use asymmetric encryption to verify identity, right? The server presents like a digital certificate and a public key.
Yes. The server proves it is actually who it claims to be. This prevents someone from intercepting the traffic and impersonating the site.
Okay.
Then, your browser uses the server's public key to encrypt a brand new, randomly generated secret key and sends that back. Because of the complex math involved, only the server's private key can decrypt it.
Wow.
Yeah. And once the server unlocks that, both sides now share a unique temporary symmetric key. From that millisecond forward, all the data, the HTML, the passwords, the credit card numbers, is scrambled into absolute gibberish using that shared key.
So to anyone eavesdropping in the middle, the traffic just looks like completely random noise.
Precisely. Total static.
So DNS routed us, port 443 let us in securely, and we've established our encrypted tunnel. Now, what actually flows through that tunnel? Because this is where the blueprints dive into the client-server model, the constant rapid-fire dialogue between your local machine and the distant host.
Yeah, this is the core engine of the web. The client is your web browser generating requests. The server is the host machine generating responses. And the interaction operates on a strict four-step cycle: request, process, response, and render.
So what does this all mean? Let me try out an analogy on you because I'm trying to visualize this cycle. Tell me if this works.
Right on me.
Is this basically like ordering food at a restaurant? It sounds like my browser is the customer sitting at the table making a request saying, I'd like my account dashboard, please.
Okay.
The server is the kitchen in the back doing the processing, gathering the ingredients. The waiter delivering the plate is the response. And finally, me taking the food, organizing it on my plate, and eating it, that's my browser doing the rendering. Does that hold up?
It gets you halfway there, but the restaurant analogy sort of breaks down when you look at the sheer computational complexity of the processing phase.
Oh, really? Why?
Well, the server isn't just taking pre-made items off a shelf or cooking a standard menu item. HTTP is a stateless protocol, which means the server has zero memory of who you are from one click to the next.
Wait, really? So every single time I click a link, I have to completely reintroduce myself?
Exactly. So in your restaurant analogy, The kitchen isn't just cooking. It's taking your order, mathematically verifying your identity via session cookies, checking your specific access privileges against a secure database, fetching your historical data, merging it with a dynamic HTML template, and essentially rewriting the entire menu specifically for you, all in a few microseconds.
That is exhausting just to think about.
It is. The server does heavy computational lifting using backend languages like PHP or Python to construct a highly personalized response on the fly.
Which perfectly explains why we have this specific division of labor. We want thin clients and fat servers. I definitely don't want my lightweight laptop trying to run complex database queries against a billion user records.
Precisely. The server executes the heavy logic and database joins behind the scenes, packages up the finished, customized code, and sends it back in the response.
Yeah.
Your local browser is then just tasked with rendering. It takes that raw HTML, CSS, and JavaScript, parses it, and paints the pixels onto your screen so you can actually read the article or watch the video. It's a highly efficient distribution of processing power.
Okay, but this brings up a logistical question about the server itself. We're talking about the server delivering all these files, the HTML documents, the images, the media, down to my browser. But how does the server keep all those files organized in the first place?
That's a crucial part of the process.
Right. And more importantly, how do developers get the files onto the server? We talked about ports 80 and 443 for viewing the web, but the sources mention a completely different port. Port 21 for FTP. Is port 21 basically the service elevator for web developers to load their furniture into the building before opening the front doors to the public?
That's a great way to visualize it. FTP stands for File Transfer Protocol, and it operates entirely separately from standard web traffic.
Okay.
When a developer builds a site, they don't just write code directly on a live public-facing server where a single typo could, crash the site for millions of users.
That sounds terrifying.
It is. They build and test it locally on their own machines first. FTP, or securely over SFTP, is the pipeline used to push those completed, carefully organized files up to the host machine.
And the sources emphasize that these files don't just get dumped into a single giant folder. They specifically highlight standard directory structures, like having dedicated images folders, scripts, media, and styles folders.
Yes, structure is everything.
They also talk about naming conventions, like why a developer should name a file flowers.jpg instead of some arbitrary string like img_99942.jpg. I'm assuming that at a large enough scale, a disorganized file structure isn't just messy, it's actually a routing hazard.
It is a critical routing hazard. Remember, a server is essentially just a powerful computer connected to the internet. The directory structure acts as the literal routing path for the web server's core logic.
Okay, so the path has to be perfect.
Exactly. If a developer links to an image in their code, the browser sends a precise request for that exact file path. If the developer later renames the file or just drags it to a different folder without updating the code, the server just throws a 404 not found error.
The dreaded 404.
Yep. Logical structure and semantic naming from day one are absolutely foundational to the web's stability. Furthermore, when they use FTP, they drop these structured files into a specific master directory, usually called public_HTML.
Right, the sandbox. Anything inside public_HTML is accessible to the outside world, but it protects the server's core operating system files from being exposed to the web.
Exactly. It acts as a hard security boundary.
So, before a developer can use that FTP pipeline to upload perfectly organized folders, they have to actually design and write the pages. And looking at the blueprints, they make a really sharp distinction in the planning phase between a sitemap and a wireframe.
Yes, two very different things.
To me, it looks like a sitemap is entirely about information architecture. There's a flowchart showing that the home page links to the About page and the Services page, completely ignoring what the site looks like.
Right.
Whereas the wireframe is the actual user experience layout for a single page,
Yeah.
detailing where the navigation bar sits and where the images go.
That's spot on. The sitemap defines the structural dependencies and routing, while the wireframe defines the visual rendering target. But to bridge the gap between a wireframe sketch and a functioning web page, developers use HTML, hypertext markup language.
And the source breaks down the anatomy of a minimum HTML5 file. It's actually fascinating how strict the rules are. HTML operates using tags, like the HTML head and body tags, which act like containers.
Yeah, exactly.
So it's very much like Russian nesting dolls. You have the root HTML tags on the outside. Inside that, you have the head tag containing behind-the-scenes metadata like the page title And then parallel to the head, you have the body tag containing everything the user actually sees.
And that concept of nesting isn't just a stylistic preference. It strictly dictates how the browser's engine parses the code. Browsers read HTML to construct something called the DOM, the Document Object Model.
What is that exactly?
It's a literal tree of parent and child nodes in the computer's memory. If you forget to close a tag or you nest them out of order, the browser struggles to build the DOM tree. It basically doesn't know where one element ends and another begins.
And the source notes that when you leave a tag unclosed, the browser tries to guess your intentions and usually guesses wrong, breaking your layout entirely.
Yeah, it gets messy.
But here's where it gets really interesting to me. The very first thing at the top of an HTML file before any of those tags is the DOCTYPE declaration. It looks like !DOCTYPE HTML. The source mentions that if you forget this one single line of code at the top, the browser goes into something called quirks mode.
Oh, quirks mode, yeah.
Wait, so if I forget one line of code at the very top, the browser essentially throws a tantrum and just starts making up its own rules for how the page looks.
This raises an important question about browser philosophy and really backwards compatibility. It isn't a tantrum at all, actually. It is an act of extreme, almost desperate forgiveness by the browser.
Oh, really? How so? Forgiveness?
You have to remember that the web was built incrementally over decades. The strict, predictable rendering rules we use today in modern HTML5 didn't exist in, say, 1998. Back then, browsers like Internet Explorer 5 had wildly different, very buggy ways of rendering layouts.
Right, the absolute dark ages of web design.
Exactly. The doctype declaration is a flag. It is the developer explicitly telling the modern browser, hey, I wrote this code using the strict, standardized rules of HTML5. Please render it exactly as I wrote it.
Okay, that makes sense.
But if you leave that line out, the browser panics. It doesn't know if you just made a mistake or if it is trying to load a legacy website built 25 years ago.
Oh, wow.
Right. So to avoid completely breaking a potentially historic web page, the browser enters quirks mode. It intentionally turns off its modern rendering engine and emulates the unpredictable, buggy behaviors of late 90s browsers.
That is wild. It's trying to be overly helpful by acting like a time machine, but if you're a modern developer who just forgot a line of code, it absolutely ruins your layout.
Precisely. Browsers try immensely hard never to show a user a blank screen. They want to render something. But without explicit declarations like DocSite to enforce modern standards, the web would just descend into visual chaos.
Man, what an incredible journey for a single web request. We have covered a massive amount of ground today.
We really have.
We started by typing a simple URL, watching DNS perform a global cached game of telephone just to find our server's IP address. We bypassed the transparent envelope of port 80, knocking securely on port 443 to execute a microsecond TLS cryptographic handshake.
Yep.
Then we explored the heavy computational lifting of the client-server model. We saw how deployment pipelines use FTP to push securely structured assets into the public_HTML sandbox. And finally, we look at how browsers parse perfectly nested HTML to construct the DOM tree, all while relying on that little docstype flag to avoid the time-traveling chaos of quirks mode.
That sums it up perfectly.
You now know the exact mechanics of what happens behind the screen.
It really is a phenomenal stack of engineering, and it operates so flawlessly that we rarely ever notice it.
It really is. So, to you listening, the next time you open your laptop, type a web address and hit enter, take a second to visualize this massive global relay race. Picture the recursive DNS queries bouncing to your ISP, the mathematical negotiation of encryption keys, the database queries spinning up on a distant server, and your browser perfectly painting the DOM tree. All of it happening just for you in a fraction of a second.
And I'll leave you with this final thought to ponder. We just spent all this time dissecting the cross-country router hops, the cryptographic handshakes, the server-side processing, and the visual rendering required for just a single click.
Right.
Which, as we noted, happens in roughly 300 milliseconds. If this incredibly complex, mathematically intense journey happens that fast, just for your one request, imagine the mind-boggling scale of physical infrastructure, the millions of miles of deep-sea fiber optic cables, and the sheer raw electrical energy required to support billions of human beings doing this simultaneously every single second of every single day.
It is absolute magic, built entirely on structural engineering. Thanks for joining us on this deep dive.